for the subject of chapter 36. So that's the last chapter for this quiz, although we will be getting to chapter 21 and electrostatic forces next week. That won't be on our quiz for 2 weeks from today. So, in diffraction, basically what you have is instead of light rays bouncing off of a surface or bending as they travel through a transparent medium, we have, in this case, the curving of light around a boundary. So that's our third and final way in which we can use the principles of optics to analyze light from different sources. Now, in order to understand why light could curve around a boundary, what we need to look at for a second is what's called Huygens principle. Basically, what we define as Huygens principle is this idea that every point on a wavefront could be considered a point source of radiation. So here would be our wavefront. This might be like a peak of a wave, but every point on that wavefront could be considered to be a point source of radiation. In this case, light radiation, but it could also work with water waves too. And so just imagine that this, instead of being a light wave with wave energy that's moving this way at the speed of light, this would be like a wave crest. This would be another wave crest. This would be another wave crest. So it would go like this, and then down, and then like this, and then down, like this and down. So this would be your plane wave front moving through. Along a plane wave front, what's the direction of the rays relative to each other? Parallel, good. So the rays are always parallel in a plane wavefront. So that means that anytime you look at a distant object, like the sun, it has rays going off in every direction. But by the time it gets to the Earth, only those rays that are pretty much parallel to each other are going to get there from the sun. And so that's why we say that distant objects produce plane wavefronts, to a good approximation. And so imagine then that this is like a water wave, and I've got a stick. And I move that stick up and down to produce a plane wavefront. Then just imagine that that stick is actually an infinite number of point sources, which can each disturb the water and produce little concentric ripples. So Huygens principle is just telling us then that every point on the wave, and I'm just drawing a few of these points here because I can't draw an infinite number of them, that every one of these points on the wavefront could be considered to be a point source for radiation. And then the rays, for example, from this point source down here would be going that way, but the ray from this one would be going this way. So the vertical components would cancel. So what you'd be left with is just a horizontal component. you have the cosine theta and the sine theta components. And the sine theta components would cancel, and that just leaves you with something that's still moving in the same direction. Similarly down here, this point, it'll shoot off a ray this way, but then this point will shoot off a ray that way. And so you can always find complementary points on an infinite wavefront where the vertical components are going to cancel and the horizontal components are going to add. And so what that does is that just allows the wavefront to continue moving in the same direction with no deflection. But now, look what happens if you create a barrier so that you don't allow the waves to travel in the bottom part of this. So I'm going to put a barrier here so that these waves can't do anything. They just hit and they're absorbed or reflected or whatever. And so then these waves up here, this one's going to shoot off a wave that looks like that. But then this one that would cancel out the vertical component is gone because it's been blocked. So it doesn't have its counter part down here to cancel out the vertical component. And so the net result of all of that is that the wave energy will curve around a boundary like that. And so this happens in harbors a lot of times because the wavelength is long enough for you to see this. If you've got a little harbor opening here, after a while, there's a lot of swell. The waves come in like this, but diffraction allows for the wave energy to curve throughout the whole harbor. And all the boats then can start shaking up and down and even get sunk if it's a bad enough storm. They're not just traveling in straight line paths anymore because you have created a boundary that cancels out the complementary point that would cancel out that vertical component. And so that vertical component still survives and allows for the wave to curve. So that's the reason why diffraction works. And you say, well, if that's true, then how come we have a well-defined shadow? You would think that you wouldn't have a well-defined shadow if the light waves are curving around the boundary of your body. And so it's not perfectly well-defined. There's a little bit of fuzziness to it, but we can't quite see it because the wavelengths are small. And so when we want to use diffraction in light, we need to make sure that these barriers are relatively closely spaced to each other. And so we can look at how that will work as we go. But with a regular shadow, you'd say, no, the light's just traveling in straight lines, and then there's no light down here. But the diffraction does allow for a little bit of bending. Okay, so how does this work then? Well, you can see here that if the wavelength is long, we get a lot of curving. But if the wavelength is short, not so much. Okay, and so light waves then, where the wavelength is way smaller than the width of the slip, and then the rest of this is a boundary, is allowing for pretty much straight line ray paths, whereas the bigger the wavelength is, the more the bending is. But we can use this to our advantage if we can make this sensitive enough, because red light has a longer wavelength than blue light does. So that means that we can get red light to curve more, blue light curves less, and so we can get a prism-like effect that's actually more accurate than sending light through a prism. And so we can use it for spectral analysis. Take light, we can break it up into its component colors using what's called a diffraction gradient. Okay, so here's another picture of that idea of Huygens principle. This is with a plane wavefront. And so the vertical components are canceling, and so it just gives rise to a new wavefront that has the same direction. But if it's in a spherical wavefront, then you can still look at the same kind of thing, and the resultant wavefront is going to expand out in a radially symmetric fashion. from a point source. And so here are some pictures of this with water. And so let's start with a simple kind. This isn't, I don't think, the way that your book starts. I'm going to start with double slit diffraction because I think it's the easiest to understand. They get into phasors and stuff right away, and kind of makes my head hurt a little bit to go through it the way that they do in the book. We can see here that, and this is with water, so we can see this better. See, with water waves, some of the light is, some of the water energy is curving. So some of it goes this way, some of it goes that way, some goes this way, and similarly with this one, so we get interference in the center. And so there's going to be certain points where we get constructive interference, and other points where we get destructive interference, because these waves are going to have different path lengths. And so in some places they add up, and some places they cancel out. Maybe not quite so easy to see the addition and the cancellation in this picture, but in this one I think it's a little easier to see. So here we see, this looks like nodes. So along these lines here, we have cancellation. And then up there too. And then in between we have addition, constructive interference. So that means that as a function of angle, you're going to expect to see a series of bright and dark spots on the screen from 2 point sources of radiation. Okay, so where are those point sources coming from? From a double slit apparatus. So here's our double slit. Here. So this is the width of each slit, A. And this is the distance between the slits, D. Like that. And so there's two types of diffraction happening. One is happening because of the differences in path length within the slit, and the second is happening because of just thinking of this point and that point as being point sources that have constructive and destructive interference. So we can look at the geometry of this a little bit and see what our condition is for constructive interference. Okay, so we're going to go to this picture now. Here are our two slits. So here's the light coming in from the back side. That's plane waves. But then using Huygens' principle, we have point sources of radiation where it's not being blocked. So it's being blocked everywhere except where there's point sources. So these point sources then produce their own radiation, and then that can interfere at a certain point on the screen to create either a bright spot or a dark spot. So that's the picture. Are there any questions about the picture? Because I know that that can be a little bit confusing. The actual math isn't bad, but I think that's true with a lot of our stuff that we do. The math is kind of simple, but the concepts are spatially sometimes a little bit challenging. Okay, so what we're interested in then is, well, first of all, we need a difference in path length between these two rays to see whether they're in phase or not. So that difference in path length if we take a perpendicular from one of these rays and drop it down onto the other, we find that that's equal to d sine theta. So d is the separation distance between the slits. And theta is the angle that we measure to the point on the screen. So here's the screen. And theta is the angle from the midpoint between the slits up to the point of interference. Now, of course, there's going to be an infinite number of points because every single point on the screen is going to have an interference path. But let's just look at the special case where we have constructive interference, because that's what we're kind of interested in. Now, for constructive interference, if the two waves start out in phase, then the difference in path length delta has to be m lambda, has to be an integer number of wavelengths for constructive interference. In other words, if one of them looks like this, and then that picks up where this one is, right? So if this one has a delta that's equal to lambda, then they're back in phase. If delta is 2 lambda, you go 1, 2, like that. And then the other wave is 2 lambda difference. Then it's back in phase again. Okay, so m is an integer then. M can be equal to 0, 1, plus or minus 1, plus or minus 2, etc. As long as we don't get to an angle that's bigger than 90 degrees. Okay, and so the amount of deflection is related to the wavelength of the light to produce a bright spot. So there you go. That's how you can determine then what the wavelength of your light is just by measuring the angle and knowing what the distance is. Then you can get the wavelength of the light just by how much it's been deflected. So here's a picture of that kind of interference. And we'll be doing this on Thursday and Friday. See that if there's no path difference, if we're right along this line where theta is 0, then they're both in phase because they're both traveling to the same distance. So that's constructive interference. That's a bright area. If the difference is half a wavelength, then that's destructive interference. Okay, so this would be, say, delta equals lambda over 2. Or it could be 3 lambda over 2. Or 5 lambda over 2. Dot, dot, dot. And that would give you a dark area. Here, for the bright area, you have delta equals either lambda, 2 lambda, 3 lambda, dot, 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 m lambda. And if m is equal to 0, then that's this case here. If this is exactly one wavelength difference, which is what it looks like here, then m would be minus 1 because it's deflecting down in the negative direction. If we're deflecting up, then it would be m equals plus 1. And so this is the kind of picture then that you would get. Say if you took laser light, that's a good single source of radiation. And we'll start with that. Take laser light and shine it through a double slit diffraction grating, you'll see light and dark bands. So this would be your m equals 0. This would be your m equals minus 1. This would be your m equals plus 1. This would be your m equals minus 2. This would be your m equals plus 2. And then this would be 1/2 at the dark spot. This would be 3/2 at the dark spot. Here it would be minus 1/2, minus 3/2. That's our integer multiple of the wavelength. that our path difference is being represented by. Now, by the way, the only way this is going to work is if the waves are originally in phase. If the waves aren't in phase, then it doesn't matter what the path difference is, because the out-of-phase nature of the waves will cause them to, for the most part, just cancel out. So what causes them to be in phase if they're coming from different points? Well, say if this is like coming from the sun. Would you get a diffraction pattern? Yes, you would. The reason why is that, and this is something we'll deal with more in 2.8c. This is normally not discussed in 2.8b, but I think it's worth mentioning, is that these are actually photons that go through both slits at the same time. So an individual photon can be in more than one place at the same time, can go through both slits, and then can interfere with itself. And so by definition, it's in phase with itself. And so that may sound very weird, but that's just the beginning of 2.8c. 2.8c starts with relativity, and then it gets into this kind of wave-particle duality, where everything that we learned about particle paths and trajectories and stuff is just thrown out the window. And you think of it in terms of these particles that can occupy, not only can they occupy multiple places at the same time, but it's required that they do. All right, so for this constructive interference then, we can say that that d sine theta equals m lambda. So that's our basic equation for constructive interference, where m is a positive or a negative integer, and it can be 0. Or sine theta we can write as m lambda over d. Okay, and so this might be, like, let's say, your bright spot for m equals 1. Let me just redraw this here. So double slit. So then on the screen here, this would be your bright spot for m equals 0. And up here, this would be your bright spot for m equals 1. And down here, this would be your bright spot for m equals 2, or minus 1. And then in between, it's actually not quite this well defined. It might look more like this, kind of fatter peaks. When you put more slits in, it starts to become better defined like this. But at first, when you just have 2 slits, that's what your interference pattern looks like. And so this is not a wave. This is brightness versus distance. So this is our m equals 1 peak. This is our 0 reference point. And so this is the central peak. There. This is the first maximum in the negative direction. That's the first maximum in the positive direction. So that's just going back to this picture. We're saying, okay, well, if d sine theta is 1 lambda, it might be here. If it's 2 lambda, it might be there. If it's 3 lambda, it might be that point up there. And then again, what you actually will measure in lab is going to be these distances between the peaks. So I could call this here, if I want, delta L, for the distance along the screen between the peaks. So that's your measurable quantity for delta L, is that value there. And that's this value here. It gets brighter there, so that's that spot. Then it gets brighter here, that's that spot. So this might be n equals 0, etc. So if we're in the small angle approximation, which we tend to be for a lot of these things, we can say that the sine of theta is approximately equal to tangent of theta. As long as, and we have to be careful here because in some of these problems, theta is not less than 10 degrees, and I'll talk about those later. But for the moment, you're going to have a small angular deflection. So you're looking at these slits here from your location, you're measuring that angle, that might be close to 10 degrees. But when you're actually looking at the slit patterns that you'll be projecting on the wall in lab this week, it's going to look more like this. Or even tighter than that. And so you're better off maybe taking the distance between 10 peaks and then dividing by 10 to get the average distance between the peaks. But you're certainly here in the small angle approximation, definitely. There's no doubt about it. And so that makes the math a little easier here. We can say that this distance here is L. That's the distance to the screen. D is the separation distance between the slits. And then we can just do a little trig problem here. We can say that this distance here is y1. Okay. Maybe I'll call this delta y instead of delta y. This is kind of in the y direction. So this distance here would be y1 from 0 to 1. Then if we wanted to go up one more, then this would be m equals 2, and then this distance here would be y2. And then delta y would be y2 minus y1. Okay, and so let's do that. Now, this relationship that I'm giving you doesn't work so well if you're not in the small angle approximation, but it works great for most of the problems that we're going to be working on. So we can just say that for m equals 1, y1 over L is the tangent of theta 1. That's just equal to 1 times lambda over d. So that's just taking this angle here, theta 1, thinking the tangent of it is opposite over adjacent for the bright spot. And we want it to be one full wavelength difference. That's the first bright spot past the central interference maximum. And so that gives us y1 is equal to lambda L over d. Then we could do the same thing for y2. y2 over L is the tangent of theta 2, which is about the same as the sine of theta. Remember, this is our original relationship, m lambda over d. Well, we're replacing sine theta by tangent theta, and then m in this case is going to be 2. So that'll be 2 lambda over d. And so that gives us y2 is equal to 2 lambda L over d. So therefore, delta y, which is the distance between the bright spots, an easy thing to measure in lab, is just going to be y2 minus y1, which would be 2 lambda L over d minus lambda L over d. That's just lambda L over d. So you're going to get these really complicated expressions in lab that have to do with sine and tangent, figuring out which n value. But you don't really need that if all that you need here is, say, to figure out the wavelength of the laser. Because you'll know what L is. That's you'll have a laser here that's firing a single frequency. It's going through his parallel beams. This is your slit. So you just need the distance from the slit to the screen, and you need the spacing between the bright spots, and then you can get the wavelength. So here, this is just delta y lambda L over d. Okay, so for diffraction to work then, we would want delta y probably not to be much less than a millimeter, right? Because how are you going to measure something that's less than a millimeter? It's not going to be easy. It's probably not going to be very accurate. And so let's say that we want to design this thing so that we can measure a delta y is measurable, and kind of measurable, 1 millimeter. But you could take, if you can see the difference between the bright spots, you could take 10 of them, you could certainly measure that and divide by 10, and that would average out your errors. Okay? And so if you do that here, then, and let's say that your L value is 1 meter. So you want L to be pretty big, because that helps to spread out your pattern. So you want this pattern not to be just a well-defined shadow. Delta y is going to be 0 if, unless you set this thing up so that you're measuring distances that are pretty small. And if you measure them small enough, then you can get the diffraction effect around a smaller boundary. Okay, so let's solve that equation. Pretty easy to solve. That's what I mean here. The math is easy, but some of this geometric stuff is maybe a little way out there, but math, not bad at all. So in this case, let's say that the wavelength of the laser is 500 nanometers. And we want to find D. If we have a measurable, delta y is measurable. So that means we can see the diffraction effect. If it's not measurable, then we can't see the diffraction effect. Okay, so that would give us D then would be YL over delta Y. So the lambda then is going to be 5 times 10 to the minus 7 meters. Remember, nanometer is 10 to the minus 9, so 500 times 10 to the minus 9 meters is 5 times 10 to the minus 7 meters. So that goes in for lambda. Then L is just 1 meter divided by delta y, which in this case is 1 millimeter. So that's 10 to the minus 3 meters. Okay. And so this is what we're putting in. We might want to put in a bigger number than this. We might put in a centimeter, if we wanted to really see the effects, but then it's going to get a little trickier. We might want to make L a little bigger. So if we plug this in, then this is going to give us 5 times 10 to the negative 4 meters, or about 1/2 of a millimeter. So if we can put the separation distance as being about 1/2 millimeter between the slits, then we'll be able to measure the bending effect of light. If we make the D much bigger than this, though, then delta y is going to have to go down. And that means it's not measurable anymore. Okay, so this is what's defining our ability to be able to measure the diffraction effects of light. Is that basically we want the distance here to be somewhat comparable to the minimum spacing between the bright spots that we can measure. And then at that point, we'll be able to determine a diffraction effect. Any questions about that? Yeah.
Does the length of the slits have any effect on it, or are we going to ignore
Yes.
it? Okay.
The width of the slits has its own effect, and that's called single slit diffraction, and we're going to get to that really soon. Yeah?
And so the distance d between the slits is measured, like where is it measured from?
From the centers.
From the centers, okay.
Yeah. And we're assuming here that d is large in comparison to the width, A. Doesn't have to be true, but it tends to be true, that d is much, much greater than A. Any other questions? All right, so with that idea in mind, then let's say that we have a separation distance d between the slits that's equal to 0.1 millimeters. Okay, so that should certainly work. That'll spread out the delta y, right? Because the delta y is divided by d. So that'll make it easier to see the peaks because you're dividing by a smaller number. So by making the d value smaller, we can spread the peaks out. And then if we do that, let's say that we get the distance between the peaks is, in this case, let's make it, trying to make this so it'll be visible light. By doing this in my head. Or distance between the peaks, the delta y value. Let's make that 5 centimeters. Let's find the wavelength of light. If it is light. It may not be light, because I'm just doing this in my head. But let's find the wavelength of light. Okay, so then I would just take this expression here. I'd say lambda is delta y times d over L. So the delta y then we have here is 5 centimeters, so that's 5 times 10 to the minus 2 meters times d. Let's keep it at 1 meter. I'm sorry, L. D must be 0.1 millimeters. So that's 10 to the minus 4 meters. I saw a number of errors on the exam that just went back to not converting units before calculating. So be sure you always do this and don't assume that the units are correct that you're being given. And then divide that by L, so that's 1 meter. So that'll be 5 times 10 to the minus 6 meters. And so that would be below visible, that would be ultraviolet radiation. It'd be about 10 times smaller wavelength than visible light, which would be about 5 times 10 to the minus 7. But that would be the wavelength that you would get from that diffraction pattern. And so it's relatively easy then to work with this equation in order to find useful information out about the light source. Now if you have more than one light source, then you can separate the different components of the light out because sine theta is m lambda over d. Okay, and so the fact that we have this relationship tells us that if lambda is bigger, theta is going to be bigger. So you should be able then to get a theta red that's bigger than a theta blue. So this would be a bright spot for red. And this would be a bright spot for blue. Blue is 400 nanometers. Red is almost double that, 700 nanometers. So bigger wavelength means more diffraction. We saw that before. Remember, like with the waves in the harbor versus the light waves. The waves in the harbor bend more, so have a longer wavelength. So red light has a longer wavelength than blue light does. And so that means that you should be able to get a whole spectrum of colors, because everything else that's in between would also be deflected at an intermediate angle. So this would be a whole visible spectrum in here. If you can get a visible spectrum, that means that you can also find the different components of wavelengths, say, in a substance. For example, maybe some kind of a molecular substance is giving off a certain wavelength of light, like mercury in this light here, or argon, or whatever. Each one of those is going to have its own characteristic set of frequencies that it's going to give off. And so you can analyze the light source. That's called spectral analysis. So this is the basis of spectral analysis. We don't use prisms. We use diffraction gradients. But there's a problem. And the problem is that the peaks are too fat. These peaks here overlap with each other with a double slit gradient. So this might be the red one, and then this might be the blue one. Oops. Then this one in the center would still line up. But the blue would be deflected by a little less than the red, but it'd still be inside of the width of the peak. So they'd mix together. You couldn't tell which one was the bright spot versus the other one. So that's the problem that we have with the double slit gradient. So to solve that problem, we do multiple slit. So this preserves the same relationship, but it makes the peaks better defined. By better defined here, I mean narrower. Whereas this might be the kind of a pattern you get for double slit. For multiple slit, you might have a big blue one that peaks out in a distinct way from the red one, so that you can tell the two apart. So this would be the red one, this would be the blue one, but they wouldn't be overlapping with each other in a way that would cause you to say, well, I don't know which one is which. I can't tell the difference between them with double slit. With multiple slit, then that's going to look a lot better. So if we go to our multiple slit grading, it's going to look like this. It's going to have many slits, but it's still going to satisfy the same angular relationship. So we can still say here that sine theta is m lambda over d. So that's still true, but for multiple slit, you have to calculate d. So we need the slit density. And so the slit density is just how many slits, say, per centimeter are we talking about. And so they have etching processes in which you can get, like, for example, 8,000 of these slits into 1 centimeter. Okay, and so that is the way then that you can make these peaks become better defined. And so that's what you would always use then in a spectrometer, would be a multiple slit diffraction gradient and not just a double slit. Okay, so let's say that for our example, we have a slit density that's 8,000 lines per centimeter. And let's find the angular spread in the m=1 interference pattern for visible light. So what do I mean by that? Well, let's say that you have a spectrometer here. And that spectrometer, here's your multiple slit grating, right here. Here's your multiple slit grating. This is just a lens. You have a point source at the focal point for this lens, and so then that sends it off as parallel beams. So you want it to start out as parallel beams, and then you're going to deflect through various angles. Then you're going to sweep across here with your little telescope eyepiece and pick up where the bright spots are, so that you can tell. That's like the characteristic signature of an element, is where are its bright spots. You know, where does it produce, say, red light and green and blue? What are the intensities? Hydrogen's got 3 spectral peaks. And so it's just basically your blueprint for figuring out what the characteristic signature is for each element that might be in your sample, if that's what you're looking for. So that being the case, let's figure out this, the distance d. And that's pretty simple calculation. It's just 1 over the slit density. Okay, so in other words, let's just think about this logically. If you had 10 lines per centimeter, then the spacing would be 1/10 of a centimeter. That'd be 1 over the slit density. Because if you had 10 slits per centimeter, then that means each slit must be just 1/10 of that, or 1 over the slit density. So we'll just do this with a bigger number, like 8,000. And that'll give us d is equal to 1 over 8,000 lines per centimeter times, now we've got to convert this to meters because we want this all to be in MKS units. So this would be 100 centimeters per meter. So when we work that out, that gives us 1.25 times 10 to the -6 meters. So this is about maybe 1/10 the thickness of a human hair. Okay, so that's pretty thin. It's 1.25 micrometers of distance between each of the slits. And so if we're dividing by a smaller number, can you see that that's also going to expand the angle? Because if we divide by a smaller number, then theta gets bigger. So by doing this, we can't use the small angle approximation anymore because our angles can be more than 10 degrees and oftentimes will be. So to do this for visible light, then we could say the sine of theta red is equal to 1 because we're looking at the m=1 interference peak times lambda. Lambda for red is 700 times 10 to the -9 meters divided by d, which is 1.25 times 10 to the -6. And so that gives us, do that for red light, 0.56. So theta red would be the inverse sine of 0.56, and that ends up being 34 degrees. Okay, so for red light then, this is going to be 34. What about for blue light? Well, we want to do the same thing for blue because we want the angular spread. So this is going to be theta red, let's say up here. This would be theta blue. We want to know through what angle are we going to sweep our little telescope to see all the colors of the spectrum, going through the whole rainbow of colors from a continuous spectrum like the sun. Okay, so for blue, we do the same thing. We say the sine of theta blue is equal to 1 times 400 times 10 to the minus 9 meters divided by 1.25 times 10 to the minus 6. And that gives us a smaller number for blue. I didn't punch that out, but I think something like I remember the answer. It's the inverse sine of this. It's about 17 degrees. And so our angular spread then is delta theta is equal to theta red minus theta blue. I'll put approximately here. You can double check that if you want. But that would be about 17 degrees, approximately. So that's the angle that you'd sweep out in going from the blue light here to the red light here. But then everywhere else in between, this would be yellow, then this would be orange, red, orange, yellow, green, blue, and violet. Actually, what I'm calling blue would be violet. That'd be the highest frequency that you can see. Any questions about that? Okay, so I think that's enough new material. Let's go ahead and take a quick look at our group quiz. Now,